Welcome to Chapter 18. We're going to begin by talking about acids and bases, their strength, and what the variety of acidic, basic, and neutral solutions are. So first, some definitions. Acids donate hydrogen, and bases accept hydrogen. And you'll notice that those are hydrogen ions that are missing their electrons, so it's just the nucleus that's being donated or accepted. When we look at a chemical reaction, we can ask which one is an acid and which one is a base. So number one here, we have HBr plus H2O, and once they've reacted, they go to H3O plus and Br minus. So which one donated hydrogen? In this case, it would be the HBr because it's gone on the product side. And which one accepted the hydrogen ion? Well, the H2O now has an extra hydrogen and a positive charge, so it accepted the H+. So your HBr is an acid. It's called hydroboric acid. And the water, in this case, is acting as a base. In number 2 here, we have H2SO4 plus NH3, and that goes to HSO4 minus and NH3 plus. So which one was the acid? Which one donated an H plus? You'll notice that the H2SO4, once it reacts, it has an extra electron, but it's missing a hydrogen. So it donated the hydrogen, and that's actually called sulfuric acid. And then we have NH3, and it accepted a hydrogen, and that's what made it both have an extra hydrogen and the positive charge. There are a few things that can act as both acids and bases. Water is a great example. It can accept a hydrogen or donate a hydrogen. Ammonia, NH3, can also accept a hydrogen or donate a hydrogen. And HSO4 minus can both donate that last hydrogen or accept another one to become sulfuric acid. When they can do either way, both donating or accepting, then they're called amphiprotic. In other words, they are able to do the protons by accepting or donating. Acids donate those protons, bases accept them. So there's something we can look at to give us a tip-off. Acids will have H and then some other elements, usually nonmetals. Bases have some kind of elements, usually metals. Sometimes NH4 will also be there, NH4OH, which is nonmetals, but it acts like a metal. And then OH. So those will be a base. If you react an acid with a base, generally what you get as a product is a salt and water. So they call this a neutralization reaction because salts don't have an acid or base portion to them, and water is neutral in its pH, which is something we'll talk about a little later. So if we take hydrochloric acid and sodium hydroxide and combine them, we get sodium chloride and water out. So that's the salt and water. So this is a neutralization reaction. When you do these, you will end up just combining the metal and nonmetal portions and then creating water as well. So see if you can write the products for these two reactions here. You'll notice the second one is going to end up giving you two waters and calcium sulfate out of it as a salt. Not all acids are equal in their strength. Your strong acids lose that proton really easily, the H plus really easily. And they do it easier than water. So if you put them in water, they separate out in that water into the H plus and whatever the other portion was, like Cl minus or something like that. There's a complete transfer of their protons to the water, and no undissociated molecules are left in solution because they dissociate easier than the water. They dissociate and make hydronium ion, H3O+. So the H pluses they give off are then taken by the waters to make H3O+, and it makes it an acidic solution. So your strong acids, and you either need to make good note of them or memorize them, are going to be HCl, HBr, HI, H2SO4, HClO3, HClO4, and HNO3. Those are the only ones. There are only 7 of them. Weak acids, when you put them in water, part of them will dissociate, but not to 100%. And they can move back and forth between being an acid or being the base that results when the acid donates the H+. Strong bases are similar to strong acids in that they dissociate completely, but they remove H+ from water, making hydroxide ions. So your conjugate acids don't donate H+ in this case. They actually are making OH. So your strong bases include all of group 1 with OH and lower group 2 with OH, starting with calcium. So that would include lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, francium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide, and we have our AOH2 as well. In water, water can react with water to make H3O+ and OH-, so an acid and a base. You'll always have a small amount of that taking place in water. Not a lot. The concentration, if you were to take the concentration of both the acid and the base and multiply their molarities together, it would give you 1.0 times 10 to the negative 14th molar of these acid and base amounts. Be molar squared. It's the final unit. So if you know how much acid you have in the water or how much base, you can use it to calculate the concentration of the other ion, because they always multiply in water to give 1.0 times 10 to the negative 14th. So if I have, for example, H3O+, and I know I've got 1.0 times 10 to the negative 6th, well, if you remember when you're multiplying, the powers add. So negative 6 and what number would give you negative 14? Your H3O+, if your OH- is negative 6, is going to be negative 8, because negative 8 and negative 6 add to give you negative 14. So your H3O+ in that case would be 1.0 times 10 to the negative 8th. If instead your OH- was 1.0 times 10 to the negative 2nd, then the H3O+ would have to be 1.0 times 10 to the negative 12th, because negative 2 and negative 12 give you negative 14. If you have an OH- concentration of 1.0 times 10 to the negative 7th, then negative 7 plus negative 7 give you negative 14, so your H3O+ would be 1.0 times 10 to the negative 7. So they'd be identical. When that happens, you've got a neutral solution, same amount of acid and base. You can do the same thing for your OH- concentration. If you're given H3O+, still has to add to 14. So if we had an H3O+ concentration of 1.0 times 10 to the negative 12th molar, then we would have to have a concentration of 1.0 times 10 to the negative 2nd for our OH-, because negative 2 and negative 12 give you negative 14. If we had instead for our H3O+ 1.0 times 10 to the negative 2 molar, then we'd have to do a 1.0 times 10 to the negative 12th for our OH-. And once again, if the H3O+ has a neutral concentration, so does the OH-. So these always add up to that beautiful power of 14 in their molarity, because the water evens it out and always keeps it right there. When the concentration of your hydronium, or H3O+, is higher than the concentration of hydroxide, or OH-, then your solution is acidic. When they're the same, then your solution is neutral, and that will always be at a concentration of 1.0 times 10 to the negative 7th. And When the concentration of hydronium ion is less than that of your OH minus, then you have a basic solution. So typically, your H plus concentration runs from 1 molar to 1.0 times 10 to the negative 14th molar. So if we were to look at two different concentrations and ask what's the difference in those concentrations, we'd notice that it's actually powers of 10 as we move out. So the pH scale puts the concentration in a logarithmic scale between 0 and 14. This is something you may have seen before with your earthquake amounts. When they're talking about an earthquake, that was a 7, that was an 8. They'll always say, well, this one was an 8.4, which is 100 times stronger than the 6.4 that we had 5 years ago, So it multiplies by 10 each time you add a number to that. So if we wanted to calculate the pH for these H plus concentrations written to the right there, we would take the negative log of the concentration, and what that gives us is the power. So, and it also changes the charge of the power from a negative to a positive. So 1.0 times 10 to the negative 12, if you were to take the negative log of that number, it would give you 12. 1.0 times 10 to the negative fifth, you take the negative log of that number, it gives you 5. So see if you can do the other two there. If you get a pH of 0 to 7, then it's acidic. 7 to 14, you've got a basic solution. And if you have a pH of 7, then the solution is neutral. So there are the answers for you. Just to give you an idea of how that pH scale works, lye, which we often use to clean drains, has a pH of 13. It's extremely basic. Ammonia, which is often in your Windex, is about 12. We use that for cleaning as well. Milk of magnesia, which is what you drink when you've got an upset stomach to calm your stomach. Since your stomach has acid in it, we're calming the acid, you add a base. So it's magnesium hydroxide that you're adding. The pH is about 10.5 for that. Alkaline or basic soil is going to be above 7 somehow. Baking soda is about 8.5. Seawater is about 8.3. Human blood is slightly basic. It's about 7.5. Neutral would be at 7. Milk is about 7.3 or so. And theoretical pH of rain is supposed to be about about 5.8. It's supposed to be about 5.8. And acidic soil is usually 5.5 to 6.5. Tomato juice, about 4.5. Apples, about 2.9 or so. Vinegar is going to be about 2.5. Lemon juice is about 2.1. The most acidic rainfall recorded in U.S. history was actually about 1.5, which is really nasty. Battery acid is about an acidity of 1. So as you go to the right, you'll find things that are more sour because we tend to biologically taste things that are acid as sour. As you go to the left, bitter is what you would taste. And at the extremes, of course, you get burning along with it because it's doing damage to your tissues.